We now turn to section 9 and the planning of future studies using Monte Carlo simulations. For instance, to estimate the power to detect that an effect is different from zero, but more generally to assess the quality of our estimation. On slide 80, we ask how power can be increased to reject that cross-lagged effects are zero. And we saw that this was an issue for the bivariate analysis of suicide and substance abuse. We found that we could not reject that the cross-lagged effects are zero, and we alluded to the fact that we may want to increase the sample size in a future study. Another alternative is to try to reformulate the variables to increase the prevalence. It was about 15 to 20% here, and maybe you can formulate questions that reflect less severe, more moderate behavior on the path to the phenomenon that you're interested in studying. And a very obvious idea is to measure more often. For instance, fall and spring instead of annually, doubling the number of time points for a given time distance, time span. And that then would double the number of time points that you use, and that's particularly useful with time invariance imposed on the model, where you benefit from a large number of time points. Or you can try to formulate multiple indicators in a factor analysis measurement model and consider effects for the latent constructs, bringing the analysis down to the continuous variable situation, albeit for latent variables. But that, of course, brings its own difficulties in terms of fitting a factor model for the measurement part. Now, a critical question then is how large does the sample need to be to make more cross-lagged effects significant? And we're going to rely on a statistical fact that in simulations, if you quadruple the sample size, you would halve the standard errors. Halving the standard errors then perhaps leading to finding significance, whereas with a smaller sample, you would not find those effects. So we're going to take a look at what you can do with Monte Carlo simulations. So on slide 81, we ask the questions. The main question, what sample size and number of time points are needed for estimates and standard errors to be trustworthy? And we looked at that a little bit earlier on slide 57 in the case of a single process, what I call a univariate analysis. Single process and using WSMV. And we pointed out which N and T were needed for good quality estimates and standard errors. And we also said that Bayes performed a little bit better. It has lower standard errors, lower variability of the estimates. And that's because Bayes is a full information estimator, just like maximum likelihood is, whereas WSMV is an estimator that uses only second order information, that is information from pairs of variables. But now we're more interested in the bivariate case, that is looking at two processes going forward. So the advantage of Bayes may be larger here in terms of having less variability of the estimates. But also WSMV, when you have a larger number of variables, it will need an increasingly larger sample size to behave well, to estimate the standard errors correctly, to match the variability of the estimates. So a second bullet then here is that focusing on power. At which sample size and at which effect size can you detect an effect if it exists, a cross-lagged effect, for instance? So we ask, what is the power? And in the Mplus Monte Carlo simulations, that's shown in the last column, presents significant coefficients. And you can also ask how much larger N and T have to be to detect an effect when the prevalence is lower. Perhaps looking at a more rare event than in the suicidal ideation situation. And also turning it around, how much smaller can N and T be if prevalence is higher? like going from 20% up to 50%, for instance. And you can also ask how large N and T have to be for model fit assessment to be trustworthy. And how large do N and T and effect sizes have to be for time invariance testing to be trustworthy? We did time invariance testing for the bivariate models for suicidal ideation and substance abuse. And that has to do then with the quality of model test, the Wald chi-square test. Now you can also ask how much larger do N and T have to be to distinguish between competing models, because we saw, particularly for the suicidal ideation substance abuse, that it is in some cases hard to distinguish between competing models statistically. Some background for doing these Monte Carlo studies is given in that old paper from 2002 that I and Linda wrote on Monte Carlo studies in structural equation modeling. Turning to slide 82, we're going to take a look at simulations related to a particular model using Bayes estimation. And we can take a look at the non-invariant DRIAR12 model. And to remind you, that is a classic dynamic model. That is, you have regressions between the y's, well, in this case, y stars, although you've added a random intercept to it. So you don't have that separation of within and between that the RI CLPM model has, but you do have a random intercept. So that was one of the models that we considered. Here we're looking at the estimates of y on z itself and on z. We're not looking now at z on y, but only y on z. And you have the estimates here. Let's focus on y on z. Small estimate, and we don't have an asterisk out there, which means that the Bayes credibility interval spans 0, covers 0, so it's not in ML terms, frequentist terms, it's not significantly different from 0. Same thing here, not significant, not significant, not significant. Then we come down to y6 on z5. There we have our first significant cross-lag coefficient in this model. And we're going to take a look at, and that's the only one, we're going to take a look at the column estimate divided by standard error. And we are going to use that as so in the same way that we think of z-tests. So the standard deviation here is the posterior standard deviation in the Bayesian analysis. So it is 0.090, but we can think of that approximately as a maximum likelihood type standard error. So you look at the ratio of 0.233 divided by 0.090, and we find that that is then greater than 1.96, whereas the first one here is not. So that often agrees with the significance that Bayes gives. This one is not significant, no asterisk there. This one is significant, asterisk there. This one is less than 1.96, not significant, no asterisk there. And then you can ask yourself, what would happen if we could quadruple the sample size? And that's what we have in the last column. That is, quadrupling the sample size gives half of the standard deviation. And we see then that then this coefficient, 0.122, becomes significant in this sense of being greater than 1.96. And so does this. Of course, this one gets even bigger. So let's do a couple of simulations here. Let's first do it for the real sample size that we used, and then go up and increase the sample size. So we look at the same coefficients here that we looked at, y5 on z4, y6 on z5, and y7 on z6. And we look at the last column, and we find then that only in 43% of the replications did we find that this was different from 0. So the power to reject that this value is 0 is only 43%. And we want it to be at least 80% by standard rules of thumb. We get a value greater than 0.8 for the coefficient that was actually significant in the real data analysis. You can look at this coefficient, the lower one, and there we have 61% power, and not quite 0.8. So this is how you can play with the numbers. Of course, the standard errors here in this analysis are lower than in the real data run because the real data model doesn't fit perfectly, whereas here we've generated according to the estimates of the real data analysis. So the model that generated the data is the correct model. By the way I do this is to run the real data analysis, ask for S values, and then use those S values in the simulation as the true population values that generate the data. Turning to slide 84, we have quadrupled the sample size. 3,000 is approximately 4 times 737. That magnitude. And look at the power here for the 4 cases. They're all above 0.8. And here's an asterisk because that was the only coefficient that was significant in the original analysis. But here, with that high power, we are likely to find significant effects, significance also for these coefficients, which are lower. We actually don't need that large of a sample size because we only need, the rule of thumb is 0.8, so we can go down to sample size 2,000, and then we find this power, 82, 95. Still a little bit above 0.8, but you may want that because these simulations are done without any missing data, without any attrition across time. So you will get lower power if you add missing data features to the simulations to reflect what's happening in the real data. So you may want to either add that missing data generation into the simulations, or you can just say overestimate the power a little bit here, so to be okay with it being being sufficient for the real data analysis with missing data. Now let's look at another case, another model, the non-invariant RIAR12. So this is RICLPM with autoregressive, an autoregressive model of order 1 for the first process and order 2 for the second process. And still, this is a base analysis. So here we're talking about y hat on z hat. And there, the only significant value was, again, for y6 on z5. That's the only one that we gave an asterisk. By the way, when we look at these results, we also see an interesting feature here. Y2 hat on z1 is negative. Not significant, but negative. And this is also slightly negative, not significant. Close to 0. And only here, starting with y5 or y5 hat on z4, there we get positive values. Larger one here, positive, larger one there. So we have a situation where maybe if we focused on the last 5 time points, y4, 5, 6, 7, 8, those 5 time points, and hold the cross-slide effects time invariant, maybe we would find significance. But then, of course, you would need to have a substantive reason for why there is this change over time in the relationship between the two variables. The substantive explanation, that makes sense. Now focusing on this effect then, which is significant, in the simulation we would get just above 80% power. And we did find it significant. So, I mean, we had an 80% chance of finding it significant, and we did find it. Now, if you quadruple the sample size then, 3,000, you would find that it is, you get power 1 here, but you find that also get a significance for this lower estimate, 0.165. And in fact, you also get significance for this negative value, which is a little bit hard to explain, but that would be significant. Now, let's turn to slide 88. And here we're taking a look at the power to reject time invariance of cross-lagged effects and contemporaneous residual covariances. So this has to do with the model test, that the Wald chi-square that we talked about. You can do simulations of that as well in Mplus. We're looking at two things: results for the CLPM2, or what we call the AR2 model, using WSMV on the left, and RI CLPM or RI AR12 for base on the right. So how do we read these results? So these are results from a simulation. First, remind us that the real data Wald test with 19 degrees of freedom is 27, and that comes from slide 73 for WSMV, which means that we could not reject invariance across time of the cross-lagged effects or the contemporaneous residual covariances. Now, if you simulate data according to these parameter values, you get the 19 degrees of freedom, but the mean chi-square is much higher, 59 instead of 27. So the simulation would say that you would reject invariance. And in fact, at the 5% level, the bolded number here at the bottom, you have 99% chance of rejecting this invariance. So we have a discrepancy here between the real data situation and the simulated data situation, which then raises the suspicion that we don't have enough power to reject time invariance for the sample. I'll get back to that. On the right, we have the RI CLPM base estimates. So that's the same thing as we show on slide 74. And in the simulated data with the same degrees of freedom, we found a much higher chi-square value. We would reject it 94% of the time, whereas we couldn't reject it in the real data. By the way, outputs for these simulations are on the website for our Webtalk. You can take a look at how they're done. So on slide 89 then, we conclude, or we ask, is the power to reject time invariance in the real data too low due to the sample size and prevalence not being large enough? The simulations show that the power is high, assuming the model is correct, which it is in the simulations. But the real data analysis has larger standard errors due to the model not being exactly correct. It therefore gets lower power. So the conclusion here is that the power to reject time invariance may be low in this case. I don't know which factor is the most important, the low prevalence or the sample size or the effect sizes. But here we find that we cannot trust the invariance testing. And that could be useful to know, of course.